Hi, if you are watching this video, I assume you have heard of neural networks but would like to learn more about it. And I plan to teach that from scratch. So this lecture is divided into two parts. In the first half of it, I will help you build a logical intuition about neural networks. And in the second half, we will go into the mathematical details of implementing a neural network by actually building a very simple neural network for binary classification from scratch. I am Dr. Sridhar Panat. I am a PhD from MIT and graduated from Indian Institute of Technology, Madras, with my bachelor's. And I'm also one of the co-founders of Visuara AI Labs. Because neural networks are so popular, you might have already heard of several technical terms about neural networks, and you might have heard it so frequently, but still probably won't have a great idea what exactly are those. So let me just state 10 questions that we might be interested in. I definitely had these questions when I was first learning about neural networks. How did people come up with the idea of neural networks? Is it something natural? Is there a logical way in which mathematically we will arrive at this idea of neural networks? Let us briefly go through that in the lecture. The mathematics behind neural networks, it looks a bit hard, and I definitely felt that it was a bit difficult to understand the theory behind neural networks. Can we sort of simplify this? I had heard people say that linear algebra and calculus, they form the basics of neural networks, but initially I did not have a very good idea why exactly is that the case? Where exactly is linear algebra and calculus coming into picture? And we'll see that in this lecture. Sometimes I had heard people say neural network is essentially like a single large function or basically a composite function. And why exactly is this the case? I did not know. We'll see how this is happening. What is back propagation? You might have heard of this. What exactly is propagating backwards? How do you calculate this? Why is this needed? And gradient descent is another very popular terminology which you might have heard of. Gradient of what? Where is it descending? How is this calculated? You might have heard of several technical terms like weights, bias, learning rate, cross-entropy loss, hyperparameters, etc. But you may not have a really good idea what are these. Even if you have not heard of these form the basics of neural network. You might have heard of activation function. What is that? Why is it needed? I had heard that chain rule is so useful in neural networks. What exactly is chain rule and where exactly is that used? And many people say neural network is essentially like a black box. Why is that the case? Why do we call neural networks as black boxes? We'll see that. So what we will do is, instead of answering these questions directly, we will simply go through the logic behind neural network, and automatically we'll see that these questions are getting answered. And at the end of the lecture, we'll come back to these and brainstorm about these questions a little bit. But now let's get into the lecture. Let's imagine we have some images of some switches. This is an on switch. This is in the off position. So the same switch in the on and off position. Assume that, this is a schematic, but just assume this is an image. Here is another type of switch. It's again very much the same thing, but slightly different design. On and off position of another switch. Here is another two images for on-off switch. These are three different images of switches. What if we want to build a binary image classifier? And what this image classifier is supposed to do is, if any of these 6 images, so there are 6 images here, right? If any of these 6 images is an input into that classifier, it should tell me whether this switch is in the on position or off position. So basically, it's like a binary classifier. It decides whether the switch is in on position or off position, right? What if we want to build something like this? So firstly, let us look at how these images can be represented. So for the purpose of making this whole thing simplified, I will just use 4 pixels to represent each of these images. So let's see how each of these can be represented as 4 pixels. This can look something like this: 4 pixels. The top 2 pixels are green, bottom 2 pixels are empty. This can look like this. Now this image has like a aspect ratio which is not like a square. It's more like the height is a little bit bigger than the width, right? So maybe this can look either like this or maybe like this, right? One of the pixels in the top row is green, the other pixels are kind of empty. This can look like this or this, right? And the 4 pixel representation of this image, these set of images, will also basically look very close to these two, right? So these are the 4 pixel representation of these images. And let's also convert this 4 pixel representation into black and white. So the black and white images would look like this. And now let us just group these just to see what is the pattern. So we have the black and white representation of the colored 4 pixel image. And when we group this, we can see that all of these are 4 pixel black and white images for the case of switch being on. And all of these are 4 pixel black and white images for the case of switch being off. So clearly there is some kind of pattern here, right? So let us represent the image in terms of numbers. So this is just an image, but we want to represent this in terms of numbers so that computers can understand this. And let us take an assumption that black means 1 and white means 0. In reality, we usually use white as 1 and black as 0 in the pixel representation, or sometimes 255. The value of white, completely white pixel would be 255 and completely black would be 0. But let's keep it simple here. Since these are the filled pixels, let's call it as 1 and the others are 0. So the corresponding numerical representation of these 6 images can look like this, right? Blacks are replaced by 1, whites are replaced by 0. Now the question is there a way in which we can construct a mathematical logic using which we can identify on or off matrices? So basically what we want is these 3 matrices, which are 2 by 2 matrices, should correspond to switch on position. And these 3 matrices, which are another set of 2 by 2 matrices, should correspond to switch off. So in the binary classification, these 3 should get classified as on, and these 3 should get classified as off. Is it possible? Let's see how to build a mathematical logic for this. What we are looking for is a mathematical function. We can call that as f. And what this function is supposed to do is, if x is the input to that function, so x is the 2 by 2 matrix that we are looking at, where there are 4 elements, x0, x1, x2, x3. So if this capital X is the input to the function should give an output y, where if this y is greater than a constant c, that means the switch is on, or if y is less than the same constant c, then the switch is off. So now we have a classifier. What should this classifier do when we input this value x into this function f, which will act as our classifier? All we need to do is check the value of the output. If the output is greater than a constant, switch is on, otherwise off. So what we are trying to do here is, for these 3 matrices, whether the input is this or this one or this, we want f of x to output a generally high value, which is greater than a particular constant. In the other case, in the other 3 matrices, the function should output a value which is generally low, or which is less than a certain constant, if these 3 are the inputs. That is what we want. The good thing is, we can also represent these matrices, which are 2 by 2 in dimension. We can also represent that using a one-dimensional array. So here we are representing the same matrix as a 4 by 1 array. So this 1, 1, 0, 0 will look like this, 1, 1, 0, 0. It's like this. So what we want is, if this is the input, so we are just reshaping the input. For these 3 inputs, we want f of x to be larger than a constant, and for these 3 inputs, the f of x should be smaller than a constant. Now, so these are the conditions, right? What can this function f look like? The function f can be sinusoidal, logarithmic, sigmoid. There are so many functions. It can be multiplication by a constant number. It can be something else. So function f can be anything which operates on these numbers. And interestingly, the function f can also be such that you are doing a dot product of the input x with another array w. I'll come to that in a moment. So basically, f can also be like a dot product. So I guess the question is, what can this array w look like? So firstly, let us look at the shape of this array. So you know that for dot product of two arrays or two vectors, they should have the same dimension. So since our input x has the dimension 4 by 1, so we transform the 2 by 2 array into 4 by 1. And what that means is the array w or vector w should also have the same dimension 4 by 1. So the w can look something like this: w0, w1, w2, w3. In the neural network architecture, these w values are called weights, but let us not use that terminology yet. We'll come to that in the later part of the lecture. I'll connect all of this to the neural network architecture later, but let's only focus on the logic right now. So what we are doing is a dot product between w and x. And the way it works is it's w0 x0 plus w1 x1 plus w2 x2 plus this. And this is just a single number. So dot product is the result of dot product of two vectors is like a scalar, just a number. That's exactly what we have here. And this is in the generalized format. And the question is, what can be the actual values of w? If the w0, w1, w2, and w3 were to be substituted with numbers, what can those numbers be? Whatever those numbers are, it should satisfy this condition. Right? These two conditions should be satisfied for us to have a classifier. So let's imagine for a moment that w, which is this array, it looks like this 1, 1, 0, 0. So this is just an assumption. We are taking some values for w. There is a reason why I selected these values. You will see that in a moment. But let's assume this is what w looks like. Then basically w dot x would look something like this. So w is 1, 1, 0, 0, x is x0, x1, x2, x3. So finally, it will come down to x0 plus x1. So the dot product of w and x will look like this, where x0 and x1 are the first two elements in the input array. So now let's calculate the dot products for these 6. So we have 6 inputs, right? In the 3 cases, it's in the switch on position. 3 other cases, the switch in the off position. So when input is 1, 1, 0, 0, which corresponds to this, so this 2 by 2 is converted into 4 by 1. The output of the dot product w dot x is 2. You can do the calculation: 1 multiplied by 1 plus 1 multiplied by 1 plus 0 plus 0. In the next case, which is 1, 0, 0, 0, which is this matrix converted to an array, the output is 1. So here the output is 2. Here the output is 1. In the third case, again, the output is 1. You can check the calculation. So for these 3 cases, the outputs are 2, 1, and 1. Then for the next 3 cases, when the array is 0, 0, 1, 1, which is the one-dimensional version of this 2 by 2 matrix, and w remains the same, right? W, we had assumed that the values are 1, 1, 0, 0. The dot product is 0 because it's all getting multiplied by 0. In the next case, again, the dot product is 0. And when you substitute the third one, again, you will see that the dot product is 0. So in these 3 cases, you have some positive dot products, and in these 3 cases, you have 0 as the dot product value. So what do we have now? We have our function now. So just observe the pattern of the dot product. The function f, which is the dot product between w and x, where the values of w were 1, 1, 0, 0, will give 2, 1, 1 and as the output for the first 3 input conditions, which were corresponding to switch on. And for the next 3, which were corresponding to switch off, the function gives 0, 0, 0 as the inputs. So we can very easily define a condition like this. Whenever w dot x is greater than 0.5, that means the switch is on. Whenever w dot x is less than 0.5, that means the switch is off. You can already see this, right? So these 3 values are greater than 0.5, these 3 are less than 0.5. So this is basically our mathematical function. So From now on, we don't have to look at what is the input. All we need to do is do a dot product of that input with W. Of course, there are few other cases which I am not considering here as the input. Like, for example, if the top half is 1 1 and the bottom half is also 1 1. So, but in our particular example, since we are looking at the switch on case, it never arises, right? Switch is never on and off at the same time. So if all values are 1 1 1 1, then it does not have meaning in our context. So we are ignoring those possible values that the input X can take. But let's only take these 6 possibilities. And for this condition to be satisfied for our function, the W should be 1 1 0 0, right? So this is our function. So what we just built is a mathematical function that can perform a binary classification of these switch images, where the output is on or off, which is decided by a condition that if the constant C, which is the output of the function, is 0.5, if it is greater than 0.5, it's on, otherwise it's off. Perfect. So now let's come to the case where the output is, not just one number. In this current case, our output is just one number, and we compare that one number with a constant. In our case, the constant was 0.5. Let's look at another case now. What if we want two numbers as our output? So we don't want the output to look like just a number. We want it to look something like an array, y0 and y1. And we want to define the on condition such that if y0 is greater than y1, that means the switch is on. And if y0 is less than y1, that means the switch is off. This is the condition that we want to define. So for whatever reason, we want an output in this format. And this is actually helpful because sometimes we don't want to say with certainty that switch is on or switch is off. We just want to talk in terms of probabilities. We want to say the class 1, which is switch is on, has a probability P, and class 2, which is switch is off, has probability Q, which might be 1 minus P. So we might need these two numbers, which kind of denote the probability of switch on or switch off eventually. And for that, in the first place, we need two numbers. We cannot have just one number. So what do we do? What can we do is we can define two arrays. So previously, we just had one array W. In this case, we'll have two, W0 and W1. So previously, what we had is y equal to f of x equal to w dot x. And currently, now what we'll have is y equal to f of x equal to y0 and y1. So previously it was just a single value y. Now it will be an array y0 and y1, where y0 equal to w0 dot x. So it's a dot product of the array w0 and the input array x, and y1 is the dot product of w1 and input array x. And let's not forget what is our goal here. Our goal is to have a system where f is a function, and when we put x, which is the input array, into that function f, it should give us an output. The output should have two numbers in this form of an array, where if the top number y0 is greater than y1, then we want to say switch is on, otherwise we want to say switch is off. So we should construct a function which will allow us to do this. So this is our goal. And please remember that this is vector dot product, and the output is such that f of x equal to y0 y1 equal to w0 dot x and w1 dot x. Now, again, the question is, previously we were asking what can w look like. Now we are asking what can w0 and w1 look like, such that our conditions can get eventually satisfied. So let's have a look at that. We are taking a vector dot product, right, for y0 and y1. So ultimately, our condition that we are interested in is y0 greater than y1 when x is either of these three inputs. So these three inputs, you can see that the top two, one of the top two elements in the input array are 1, which means these are all switch on positions. So if either of these three is the input, that means the top element, which is y0, which is again w0 dot x, it should be greater than w1 dot x. And w0 x should be less than w1 dot x when x is equal to either of these three. Which are these three? It's the one with either of the bottom two elements to be 1 or both to be 1. So these are all the switch off conditions. So from the dot product, we know that W0, W1, and X should all have the same dimensions, right? Because otherwise we can't take the dot product. So W0 and W1 should have the dimension. Both should have 4 by 1 as the dimensions, because X dimension is 4 by 1. And let us take some specific values for W0. So let W0 be 1, 1, 0, 0, and let W1 be 0, 0, 1, 1. Okay. So now let us calculate the dot product. So what is our function? Our function f is in such a way is such that it outputs a 2 by 1 array where the top element of the array is w0 dot x and the bottom element is w1 dot x. So w0 dot x is the dot product between this one and this input. So this is 1 1 0 0. This is also 1 1 0 0. So the dot product will be 2. The bottom element of this output array would be W1, which is this dot product with this, and that would be 0. So the output here is 2, 0. In the next case, if this is the input, we have the dot product output. You can calculate. It's very easy, fairly easy to see that the output will be 1, 0. In the third case, again, it's 1, 0. So please note that in all of these three cases, the input X is such that it corresponds to switch being on. Now, if we look at the other three, where the switch is off, if X equal to 0, 0, 1, 1, and when we do the dot product, we see that the top element of the output array will be 0. You can see that it's the dot product between this, and the bottom element of the output array will be 2. And in the next case, the dot product will look like 0 and 1, and in the next case, the dot product will again look like 0 and 1. And these three are the input conditions corresponding to switch being off. So now we have again got our classifier. Our conditions are being satisfied because see, for these three conditions, we have arrays like this 2, 0, 1, 0, and 1, 0. And what was our condition that we were interested to build? We wanted to be able to say that whenever the output is such that y0, which is the top element of the output array, is greater than y1, the bottom element of the array, that means switch is supposed to be on. And indeed, the switch is on for all these three inputs. And in the other case, when switch is off, whenever the input is such that switch is off, the function should output in a way where the bottom element is greater than the top element. And indeed, that's the case for these three. So our goal or conditions are actually being satisfied by this function, which is excellent. So we now have a function f, which can take an input x as the array, and it will output an array of two numbers. And these two numbers can tell us whether the switch is on or off. And ultimately, these two numbers will help us predict the probability. Not yet. We are still not talking about probabilities, but it will eventually help us come to the probability. Right? This is awesome. So let us pause for a moment. Let's take a step back and recap what we were doing. We had an image of a switch being on or off. We converted that image into a 4-pixel representation, color images. So if it's on, top 2 pixels are green, otherwise bottom pixels, one of them or both could be red. We converted this 4-pixel representation into 4-pixel black and white. Then we converted that into a 2 by 2 matrix, which we converted into a 4 by 1 one-dimensional array, right? This is a 1D array. Then this 1D array, X, is input to our function. And the output which this function gives is an array which has shape 2 by 1. And the W0 and W1, which are the vectors we are doing a dot product with the input X, have these values. So these are the values which we assumed. Assume meaning we were somehow able to find these two values such that our conditions are getting satisfied. And switch is on when y0 is greater than y1 and switch is off when y0 is less than y1. So this is our, this is what we were doing so far in a nutshell, right? So let's move on. Now, instead of specifying numbers, let's try to generalize our calculations in terms of variables. So we have an input matrix 2 by 2, x0, x1, x2, x3, which we convert into x equal to a 4 by 1 array or vector. And that is the input into our function f. The function f is such that the input is taken, a dot product of the input is taken with w0 and w1. Let w0 be w0 0, w0 1, W02, and W03. Previously, if you remember just the W matrix or W array, it was just W0, W1, W2, W3. Here we have one more subscript because there is a subscript for this also. And W1 would be small w 10, 11, 12, and 13. So now we can define a dot product between W naught and X. So X is this, right? So W naught X would look something like this. Element wise dot product, W naught naught times X naught plus W naught 1 times X1, W naught 2 times X2, etc. So that is the top element of the output array. And the bottom element is the dot product between W1 and X. So this dot product is finally a number, which is the sum of these four. And this dot product is also another number. So this is dot product of W1 and X, which is this. So this is the general formula for the output Y. Now, can we represent, instead of having two arrays, W0 and W1, can we represent both of them as a single matrix? Let's see how to do that. So let capital W be this array where the top part is the transpose of the W0 matrix. So we just take all the elements of that array like this. So I mean, technically we cannot say just like a transpose, but I'm just writing it for your convenience. So essentially what we are doing is the W0 and W1 array, instead of writing it like a column, we will write it like a row, and then we will concatenate those two. So what we have is W0 naught, naught 1, naught 2, naught 3 as the top elements of the first row, W1 naught, 1 1, 1 2, 1 3 as the elements of the second row of this capital W matrix. So previously we had a W matrix which just had 4 numbers. Now we have 8 numbers because we have numbers from W0 and W1. So now let's see what is the output of matrix multiplication. So see, the symbol has changed. So this is not dot product anymore. This is matrix multiplication between W and X. So the dimension of W is 2 by 4 and dimension of X is 4 by 1. Let me just write it down here. So let me just note down the dimensions here. So this one has dimension 2 by 4. Oh, sorry. And this one has 4 by 1. And the output dimension is 2 by 1. So this whole thing is just one number. And this whole thing is another number. Right? Okay. And if you see this output, you can see that it is exactly same as the previous calculation which we did using W0.x and W1.x. This was the output. So the output of matrix multiplication of the vector, the matrix W with X is this, and the output when we had two separate vectors or arrays W0 and W1 is also this. So these two are the same. So what does this mean? What this means is we can represent this whole calculation as just a matrix multiplication. That's what this means. So what we did so far, I'm just summarizing into this one slide. And this has only just one matrix multiplication. If we have image input and we are converting that into a 4-pixel representation, black and white, converting to 2x2 array, then to 1D array. If this is the input, which is converted to the 4x1 array representation, our function f is simply a matrix multiplication. Previously, we saw that this function f was a dot product between W and X. In this case, we see that the function f is simply a matrix multiplication between W and X, where the dimension of W is 2 by 4. And what are the values? Interestingly, the values of these are the exact values which we took before. So let's have a look at that. So previously we had W0 that was equal to 1 1 0 0, right? And W1 was 0 0 1 1. So these values we are just W not, not 1, not 2, not 3, we are just putting here. And W1 not, 1, 1, 1, 2, 1, 3, we are putting here. So that is our final W matrix in terms of actual values. And if we use this as the W matrix for performing our matrix multiplications, it will satisfy our condition where switch is on if y0 is greater than y1, switch is off when y0 is less than y1. So essentially, this summarizes our whole thing into just one matrix multiplication. Okay, so let's move on. The problem with what we did so far is that we are talking with a lot of certainty. So certainty meaning we are saying switch is on when y0 is greater than y1 and it's off when y0 is less than y1. So it's like it's like one probability event. But so I'm just writing it here. So this can be rephrased as switch is certainly on when y0 greater than y1, certainly off when y0 less than y1. Can we write in terms of probabilities? What if we want to say with 65% probability switch is on, 40% probability switch is off? Because in real life, nothing is ever 100%. We usually want a probability distribution for things to make sense. If somebody tells you, hey, I have a neural network, it's classifying with 100% certainty that this is this or this. In some cases, I understand that you may have 99.999% probability, which will be rounded off to 100. But in general, you want a probability distribution for a classifier to be useful to you. We have not come to neural network classifier yet. We are still in the mathematical logic part. So the question is, how can we convert the output y into a probability? So this is our output y, right? It's an array. It has two numbers. How can we convert this? Can we say something like this? The top number p of y0, so probability of switching the things being switched on is y0. Probability of the switch being off is y1. Can we say this? Will this ever make sense? Ignore the previous conditions of y0 greater than y1 or y1 less than y0. Just ignore that. But will this make sense? We can check with a simple example, right? What if y is simply 2 and 0? Then in this case, probability for switch being on is 2, probability of switch being off is 0, and sum of the probability is 2. This does not make sense. First of all, sum of the probability should be 1 and probability should not be greater than 1. Here it is 2. So taking those values directly and representing them as probabilities, that does not make sense. So can we do something like this? What if it's a relative weight? So what do we mean by relative weight? So relative weight means probability for on is y0 divided by y1 plus y0 plus y1, right? And the probability for off is y1 divided by y0 plus y1. This maybe makes a bit more sense because the higher the value of y0, the more. So let's say y0 is 100 and y1 is 1. Then this is basically 100 divided by 101. Let me just write that just so that you can see that. So if y0 equal to 100 and y1 equal to 1, then this probability would be 100 divided by 101. And this is approximately equal to 1, right? It might be 99.999, I don't know, but it's approximately 1. And in this case, let's take this example. In the case of this, it will be 1 divided by, okay, let me move this a little bit up. This will be 1 divided by 101. And this is approximately 0. And makes sense, right? If y0 is so big, then this is what we want. Can we then use these kinds of relative weights? Is that something that makes sense? Let's see with an example. So if, let's say, again, the same condition, if y was 2 and 0, then the probability for switch being on is 2 divided by 2 plus 0, which is 1. Probability for the switch being off is 0 divided by 2 plus 0, which is 0. So here we are not violating anything with respect to probabilities. The sum of the probabilities is 1. Both of the probabilities are between 0 and 1. So we are not violating anything. All of this is sensible. But we are not necessarily getting probabilities here because this looks like certainty. If one of these values becomes 0, then the probability corresponding to that becomes 0. So it's like we are telling with certainty that, okay, 100% the switch is on in this case. So that is also not good. So we want something that looks like a probability distribution. So that is why we have something called as Softmax. Softmax is very famous. Probably you have already heard of that. It's a function which converts these two numbers into a probability distribution. It's very simple. So the softmax is literally, if y0 and y1 are the numbers, the softmax corresponding to this is e raised to y0 divided by e raised to y0 plus e raised to y1. The softmax corresponding to this is e raised to y1 divided by e raised to y0 plus e raised to y1. So this is the softmax. This is the generalized representation for softmax. And what can softmax do? Softmax can very nicely convert these two numbers to a probability distribution. I'll show with a numerical example very soon. But basically, now the probability for on is equal to e raised to, so if this is our example, probability for the switch being on is e raised to 2 divided by e raised to 2 plus e raised to 0. And when you calculate, it will be 0.88. So with 88% probability, the switch is on. And P of off is e raised to 0. Which is this e raised to 0 by e raised to 2 plus e raised to 0, which is 0.12, around 12% probability. And this is very nice because if you add these two, you can see that when you add these two, the denominator is common. So the numerator is this plus this, which means the sum of those two is 1. So probability of on and off is 1. Sum of probabilities is 1. We want that. And the probability values are between 0 and 1. And we are not saying anything with certainty here. We are saying with a probability distribution. So we have non-zero probabilities for both of these outcomes. This is very, very good. So we can use softmax to make this kind of a prediction. And if the actual values for the input x, let's say I'm just giving a random array of 4 by 1. If they are 3, 1, 4, and -5, when you plot it in the graph, it will look like this. It will span from -5 to 3, -5 to 4. -5 is the smallest number, 4 is the largest number. Whereas when you convert these exact 4 numbers into its softmax representation, it will look like this. So the numbers are all between 0 and 1. The lowest number, which is -5, is converted to the lowest number in the softmax also. The highest number, which is 4, is now kind of propelled up closer to 1. So this, indeed, the 4 has the highest probability. So the distribution the relative importance of the distribution kind of remains the same a little bit, right? This was the highest. Here, this is the highest. This had the lowest value. It's barely visible. The bar plot is there. It's because it's not 0. It's 0.00008. So it's there, but it's barely visible. And this is the second biggest, and this is the third biggest. And the good thing is, all values are positive. Unlike this, here we had negative values also. Here, all values are positive. We might need that in several cases. All values are between 0 and 1. So we are kind of normalizing the values to a fixed range. And beautifully, if you sum up all these values, the sum of that will be 1. So if you sum up 0.71 plus 0.26, which is 0.97, and you add this to that and this to that, if you add up all of, I have ignored some other digits. I have only taken 2 digits here, but basically if you add up all of this, you will get 1. So this is exactly what we were looking for, and Softmax can do that for us. So what if our image was not black and white? If we wanted to represent the image as RGB, for simplicity, we converted the RGB into black and white. But what if we don't want to do that? Then the images will be represented as follows. So we will have 3 matrices. Or rather 3 channels. So we'll have red channel, green channel, and blue channel. So using these 3 channels, we can represent pretty much any colors. And if this is our image of the switch being on, then red channel and blue channel are basically empty. There is no pixel values. It's all 0. And for the green channel, the top 2 pixels have high value, right? And if this is the image, which is in the off position, switch being in the off position, our 3 channels, R, G, and B, would look like this. Blue and green are empty, and red has maximum value in the bottom 2 cells. And these 3 channels we have to represent as 3 separate matrices. We will not go into the details of this. I just want to barely show you how this is represented, but none of our calculations will be using RGB because it's a bit complex. But let me just show you how this is represented and we'll move on. So RGB will be converted into these 3 matrices, and all the empty values are basically 0. And whenever there is a high green value, we assume it's 1. And here, all the red values, wherever there is red, is in the red channel, it's 1. All the other values are 0. So this is the representation that we have in the form of matrices, but you can see that it's three-dimensional. It has a height, it has number of rows, it has number of columns, but it also has some kind of stacks. It's like it has a depth dimension, so it's like a 3D array, and these are called tensors. Tensors can also be it can have more dimensions, more than 3, but this is what we have right now. So in a mathematical format, we can represent these tensors like this. You write matrices separated by commas and you enclose them in a curly bracket. And so if our original on image, if we had that, we will have the matrix number-wise matrix representation would be, the tensor representation would be like this. And if we had the off image, it would look like this. So these are called tensors, and the previous one is like a third order tensor. It has, in the depth dimension, it has 3 units, whereas an nth order tensor can look something like this. It will have the first one, second one, etc., up to n. In fact, here it should be, since we are starting from 0, this is technically an n plus 1th tensor. I should probably edit this. Technically, this is not correct. So this should be, let me correct this for the sake of, so this is n plus 1th order. That's easier for me. So this is n plus 1th order tensor, and okay, now I feel better because it's actually starting the count from 0 and it's going all the way up to n. All right. Now let's come back to our business. We were trying to make a function that could classify these images, right? Okay, we did all of that. So let us think about the values that we had for the W matrix or W array a little bit. We came up with these numbers which magically worked. We said the W matrix can look like 1, 1, 0, 0 or 0, 0, 1, 1. It's a bit magical, right? I did the trial and error before I was making these slides. I found that these values actually work for good classification. And is there a mathematical logic that we can use here to come up with these numbers? Is there something that we can do? So what is that we are trying to do? We have 3 conditions in which the switch is on, these 3 matrices, and for these 3 matrices, the switch is off, right? So what was our output? Our output was y0 and y1, right? It was a 2 by 1 array. The top one was y0, bottom one was y1. So essentially what we want is, if the input is any of these 3, we should generally have a high value of y0, so that when we predict probabilities using Softmax, the probability for P of on would be higher. It will be greater than 0.5. And similarly here, in all these 3 cases, the y1 should be generally higher, because then in the Softmax, the probability corresponding to y1 will be greater than 0.5. That's what we want. And if we write the entire expression in terms of variables, it looks like this, right? W0 x0 plus W0 x1 plus this is y0 and this is y1. Now let me write this down and show you. So here, can you see what the values of x0, x1, etc. are? So here, whenever our input is like on, generally x0 or x1 or both, they tend to be high, right? Because this is the green is in the top. So whenever switch is on, x0 and x1 will tend to be high, and x2 and x3 will tend to be low, which means the values of W02 and W03 are not relevant in this particular case whenever the switch is on, which means if we want an output that is favorable for Y0, which is showing that switch is on, we can say that W0 and W02 and W03 could be 0, but W00 and W01 should generally be high, so that when x0 and x1 are high, we are not driving it down back to 0 or some low number. So in general, we want W00 and W01 to favor x0 and x1 when the switch is on, so that y0 can be higher. But what about when the switch is off? When the switch is off, you can see that x0 and x1 are not the values that may be high, but rather it will be x2 or x3, because they are the bottom row, right? Bottom 2 pixels of the bottom row, which means for that case, W10 and W11 are not really relevant because they are corresponding to x0 and x1. And even if we drive it down to 0, it's completely fine because anyway x0 and x1 are not the ones who are contributing towards making this image into a switch off condition. So these two can be 0. But since x2 and x3 are important, we want w12 and w13 to have some importance in this case for y1 to be higher. So when switch is off, we want y1 to be higher, and switch is on means y0 should be higher. So how does this look like mathematically? What this means is whenever we have a switch on condition, we want x0 and x1 to be high so that y0 will be high. If switch is off, we want x2 and x3 to be high so that switch will be off. All right. So we can define like a proportionality, and basically what we are saying, what is being said here is the same thing that we discussed before. And whatever changes happen to x0 and x1 in the case when switch is on is going to directly affect the output y. And whatever change is going to happen to y1 is influenced by the changes happening in x2 and x3. So if x2 and x3 will become high, and we are assuming that for the top row w02 and w03 we are driving down very low, like it won't be very significant. And so for that reason, x2 and x3 cannot influence y0 that much. And in the second row, we will drive down the value of w10 and w11 low, so that x0 and x1 cannot influence the value of y1 that much. And here is where we enter the realm of partial derivatives. This is not in a strict sense, but essentially we can look at what we are trying to do here in terms of partial derivatives. So what we want to do is we want to have we want the y0 to be influenced by x1, which means dou y0 by dou x0 should be some high number. So basically we want w00 to be high, at least higher than 0. That is one condition. The second one is dou y0 by dou x1 should again be high. And that is, let me just do this. Since this is the y0, right? So this equal to y0. So dou y0 by dou x0 equal to w00, and let's say another example is dou y0 by dou x3 would be this w03, right? So that is the partial derivative. So here what we want is the partial derivative should be such that dou y0 by dou x0 should be somewhat high, dou y0 by x1 should be somewhat high, and for the switch off case, we want dou y1 by dou x2, which is dou y1 by dou x2 is this, w12 should be high and w13 should be high. So this is the basic mathematical logic. The logic using these partial derivatives is what we should employ for finding the appropriate values for these individual weight elements. Okay, so now and the rest of the values, which are w02, w03, w10, and w11 can be assigned 0. So this is the condition, right? So with this mathematical condition in our mind, what are some different options that we can have for the matrix W? Can we look at some of these options? Let's say matrix W is such that this is 5, 4, 0, 0, bottom is 0, 0, 7, 2, or something like this, or something like this. This was our original thing. Originally, this was our W matrix. Will all these three matrices of W, will it help us satisfy our condition? What was our condition? The softmax probability. So softmax probability for switch on should be high. And let's see. So let us calculate a Y and softmax for a particular input. So this is the W, three options for W we are considering. And let's say our X is this. X is the input. Let's say the input is this 1, 1, 0, 0, which means it's the top two cells are green. Then the function output is W times, which is the matrix multiplication of the weight, which is this multiplied by input. And the output here is 9, 0. And how do we convert this to probability distribution? We'll come to that in a moment. But before that, let's also calculate the output for this case. It will be 2 multiplied by 1 plus 8 multiplied by 1, which is 10. and the bottom will be 0 because it will be 0 multiplied by 1 plus 0 multiplied by 1 plus 6 multiplied by 0 plus another 0. And here it will be 2 0, which we already saw previously. Now let's convert this into a probability distribution. If we calculate the softmax for these two, it will turn out to be 0.9999 and 0.0001. This is the softmax. In this case, softmax will be a bit more higher because it's 10-0. So the probability for switch to be on in this case is 99.996%, and the probability for switch to be off is 0.004%. And switch is actually indeed like the actual true value of switch is on, because the top two, if you look at the input, top two are 1 1, right? And the last softmax is the one which we saw earlier, 88% probability switch is on and 12% probability switch is off. And basically all of these three values for W actually works, right? So this is good, this is good, this is also good. And this is how, using a mathematical logic, using partial derivatives, we can arrive at the value of this W. We'll see this once again, how to arrive at the value of the so-called weight matrix for neural networks, how to arrive at that using partial derivatives and of course applying logic also. We'll come to that. But just look at one thing. In this case, the switch is obviously on, but still we are not saying that 100% the switch is on. We can round this off to 100%, but still we are having a probability distribution. In this case also, again, because of the softmax distribution being 10-0, we are saying, okay, a bit more probability, like instead of 0.9999, we have one more decimal now. So this is 6. So we are saying the probability for switch to be on is slightly more higher than this. So it all depends on the weight matrix. But all these three weight matrices work. What's another weight matrix that may work? Any positive number, like this will also work. 0.2, 0.1, 0, 0. And then let's say bottom row is 0, 0, 1.3, and this let's be 4. So this weight matrix will also work, because these two numbers are positive and these two numbers are positive. Rest of the ones are 0. This will also work. And so this is amazing. So let's move on now. So what do we have? We have a mathematical logic for finding the matrix W, which will help our binary classification. And how do we do the binary classification? We simply multiply the input with the matrix W, not the dot product multiplication. It will be the matrix multiplication. Okay, awesome. So now let's move on to the next part. Whatever we did so far was to go through the natural human logic, which can be expressed in a mathematical language for performing a binary classification task. Now let's come to the main, hero of the day, which is neural network. So let's see how to construct the neural network architecture, which can do the same thing. So we'll start the neural network component by component. As you might already know, neural network is kind of trying to mimic human brain, the neural connection. So there are neurons, there are connection between those neurons. And in the neural network, we can call those neurons as nodes. So first, let's look at the input. Input is X, X0, X1, X2, X3. In this case, we'll take an input layer. So all the nodes which are present here are part of the input layer. You will get to see what exactly is this input layer in a moment, but let's just understand that we are currently focusing on the input layer. Then what we do is we pass each of these values into the input layer. So X0 is passed into the first node, X1, X2, X3 into the next subsequent nodes. So you can already see that the number of nodes in the input layer is same as the length or the dimension of the input X, right? Okay. Now there is another layer after the input layer called as hidden layer. In our particular case, we will assume that the hidden layer has two nodes, node 0 and node 1. It's just that I'm using this convention of 0 and 1. You can also call it as node 1 and node 2. Doesn't matter. But you have the input layer and you have the hidden layer. So these two nodes are connected as if different neurons are connected in an actual, human neural network. So there is a connection going from this to that, this to that. There are a bunch of different connections. And since each node is connected to each other node in the next layer, this is called as fully connected. So fully connected, input layer and output layer, hidden layer will look like this. After this, we have to assign how strong are these connections. So the connection between input layer to hidden layer, this connection may be stronger, this connection may be a bit weak, this may be a bit stronger, this may be weak, who knows, right? So this is exactly how human brain also works, right? We have different degree of connection between different parts of the brain through neural connections. Some connections are stronger, some are weaker. So let's name it. So this will be W00. All connections going from input layer to the node 0 in the hidden layer are starting with 0. So W00, W01, 02, and 03. All connections going from input layer to node 1, which is this, are starting with 1. So W10, 11, 12, and 13. Okay. Now let us look at how the output from this hidden layer might look like. So what is happening in this hidden layer is, so right now these neural connections are happening. So some signal, just like in a biological system, some signal is being sent from one layer to the other. Let's see what's happening here. What's happening in this node is a summation. Summation meaning W00 multiplied by X0. So here what's happening is whatever input is coming here, W00 X0 plus W01 X1 plus W02 X2 plus etc. So that's the summation. And here also the same summation is happening, but this time the summation will be W10 times X0 plus W11 times X1 plus W12 times X2 plus next one. In addition to these inputs, there are also something called as bias, denoted by B. So bias here in the first or a 0th node, there is a bias B0. In the first node, there is something called B1. These two are biases into these two nodes in the hidden layer of the neural network. Okay, so what comes out of this is sigma Wx plus B0. So to the summation, we add the bias. Here also, to the summation, we add the bias. Okay, fine. Now, we are almost close to being able to predict our output probabilities. So what we want is, we want a probability distribution saying that this input belongs with P percentage probability, it belongs to the first class, and with 1 minus P percentage probability, it belongs to the second class. That's what we want. So what we do is, we saw the activation before, so we will have activation to, so these numbers will be passed through an activation function. There are many different types of activation functions. We'll see that in the later part of this lecture. But here, as you might have already guessed, we will be using Softmax activation. And at the end of Softmax activation, what do you get? You will get the probability for class 1, which is same as probability P on. So what this means, if you are having probability 88 in this particular number, what that means is with 88% probability, the switch is on based on the inputs. And here it's P of class 2, which is same as P of off in our specific example, right? So this is the structure of the simplest way in which we can represent the whole thing which we did before up until this point using a very simple neural network which has input layers, output layer, and a hidden layer. Okay. Now let us take one more step ahead. And just before we do that, let us have a look at what are these things. This is just to recap your knowledge so that we are both on the same page. So firstly, nodes. What are nodes? This is a node, this is a node, this is a node, this is a node. This is again a node, right? These are nodes. Inputs are these. We have our original input, which was X. It looked something like this. X equal to X0, X1, X2, X3. This was our the original input X. And here, these are the inputs, the individual elements. We are passing that into the input layer with 4 nodes. Weights are the ones which are denoted by W. So W0, 0, 1, 2, 3, 10, 11, 12, 13. These are weights. Bias is added over here, B0 and B1. This is bias. Activation function in our case is the Softmax function. You saw that before. So I don't think we formally called this as an activation function, but that is what it is. Softmax is a sort of activation function. Hidden layer, we have a hidden layer over here. This is a hidden layer. In the output layer, we produce the softmax probabilities. So please note that in this particular example, we are not using any particular activation in the hidden layer. But usually, all the hidden layers can have another activation like sigmoid. We'll come to that in a moment. You might have heard of some of these activation functions. And finally, the output layer is this, and this is the input layer. So this is the whole architecture of the neural network that we are currently looking at. Okay. So let's move on. So what we did is we saw that neural network is a way in which the previous logic that we implemented, the mathematical function which we implemented, can be shown. So that's what neural network is doing. So previously we had an image. We converted the color image into 4-pixel representation, which is again in color. We converted this into a black and white representation, and that into a 2x2 matrix, and that into a 1D array, like this. And then we saw that we can represent this whole thing as matrix multiplication, where X is the input, Y is the output, f of X, F is the function, and the output looks like a 2x1 array. And the function W, the matrix W, which forms part of the function, a matrix multiplication is done. So which is W star X. And the dimension of W is 2x4 and dimension of X is 4x1. So the output dimension is 2x1, as you see here. And to get probability, output probability, we apply a softmax to this Y, basically softmax of W times X. Just note one thing here, we never added any bias here. So we have these weights W, but we don't have any bias here. That was not part of our natural human logic. It might have come if we had a more complex problem, but we did not take that. So softmax of this multiplied by this, which is essentially softmax of this whole array. Looks like a bracket is missing here. Okay, so we had assumed that bias is 0, but what if we had a bias? What would be this looking like in that case? If we had a bias, since there is B1 and B0 and B1, we can represent the bias as an array, B0, B1. Its size is 2x1. So bias is actually added to this. Let me show you. Bias is added to W times X. So this is W times X, and bias is added. So this is a 2x1 array, and bias is also a 2x1 array. It's added to that before taking the softmax. So the output would look something like this. Softmax of W times X plus B. So the final output Y will be W naught not X naught plus etc. plus B naught. And this will be the same thing as before plus B1. And B naught or B1 are the two bias. So this is how how you can see that the neural network, which is shown here, with 4 nodes in the input layer, with an output layer with 2 nodes with fully connected connections between the input and hidden layer, and 2 nodes in the output because you have 2 classes, and a bias. In our case, we assume the bias is 0. But basically, this neural network and this entire matrix multiplication operation which we arrived at are doing the exact same thing. Okay. Now, what we did using neural networks is that the same matrix multiplication which gave us a result for the binary classification, we are representing it in another format. So neural network is a little bit more complicated. It's actually elegant also. It makes this whole idea more attractive and appealing for sure. But ultimately, it's matrix multiplications. And that is one reason why we say, this neural networks as a concept is heavily reliant on linear algebra. We are doing a lot of operations. We are taking transpose. We are doing matrix multiplication, dot product. Bunch of these operations we are doing. We are dealing with matrices. We are dealing with arrays or vectors. So whatever our mathematical function f was, which was the W matrix, whatever it was doing, exactly that is what neural network is doing, and that is what we are trying to represent. But you will soon come to realize why neural network is a very, very powerful representation visually, because the moment this problem becomes very complex, we deliberately selected a very easy problem. The moment it becomes complex, we will need a bit more complex neural networks, and that be able to think of the neural network as this many input layers, these many output input nodes, these many output nodes, and these many hidden layers and each hidden layer has these many units. It's very powerful. So let's now move on to the next part. So we constructed the neural network, but the problem is, again, we saw that using partial derivatives, we can kind of arrive at values that are possible for W. But in this case of neural networks, we kind of pull these values again out of thin air. We know that these values work because we used these values before. So bias was 0, 0. W was like this, 1, 1, 0, 0, 0, 0, 1, 1. But we kind of pulled these out of thin air. We did not employ a mathematical logic which is relevant for neural networks yet. So let's think about what could be the logic. How can we teach the neural network to find good or appropriate values for W and B such that it can accurately classify? We had 6 different images. 3 of them were in the on class, 3 of them were in the off class. Can we train the neural network or teach the neural network to do that by finding appropriate values for W and B? So basically, this process of finding good values for W and B is called training, weights and biases. So the neural network will train itself on different input data points in this training process. So let's see a very simple example of that. So we will first start with random values of W and B. B, for example, we'll just start as 0, mainly because it's often done that way. In many cases, bias is not needed, or you would start with a 0 value for the bias, and then if needed, it will get automatically added in the training process. But for now, let's only focus on the weight values. And unlike before, so before we started the weight itself as 1, 1, 0, 0 and 0, 0, 1, 1. This time we won't do that. Let's start with some random non-zero values for W. So let's look at the neural network. So the random non-zero values are the following. So the weight matrix W, W0, 0, 0, 1, 0, 2, etc. will be 0.1, 0.2, 0.3, 0.4. This is 0.5, 0.6, 0.7, 0.8. This might very well be even other random numbers, but I just put some sequential numbers, 0.1 to 0.8. So now where would these weights go? It will go here, and the bias is 0, 0. So 0.1 is this. This is weight 0, 0. 0.2 is weight 0.1, 0.2, and 0.3, 0.1, 0.2, 0.3, 0.4, and these are weight 1.0, 1.1, 1.2, and 1.3. Okay, and bias would be 0. That's why I have not shown it here. Now, with these weights and bias being 0, let us check what kind of output this neural network will produce for a sample input. Will it be correct? Will the output have a correct probability prediction? Let's see. So let's say this is the input X. This is our first input 1. We have 6 inputs. Input 1, X equal to 1, 1, 0, 0. We know that in reality, the actual state of the switch in this case is on. So ideally, we should have a prediction where the softmax probability distribution for this should be higher than this. Previously, it was 88% and 12%. This time we have random weights, and let's see what is the probability distribution. So we'll first put the inputs 1, 1, 0, 0. Okay, and now we will calculate. So if you look at this summation, what is it? It is W times, it's a summation of W times X. So W01 times X0 plus W00 times X0, W01 times X1, W02 times X2, and W03 times X3. So that will be 0.1 multiplied by 1 plus 0.2 multiplied by 1. That is 0.1 plus 0.2, and that's 0.3. And for here, it will be this multiplied by 1 plus this multiplied by 1 plus 0 multiplied by this plus 0 multiplied by this, summation of Wx. And that will be 0.5 plus 0.6, which is 1.1. And now you might already be able to see when we take the softmax of this, the probability is such that 0.31 probability or 31% this is on, but 69% this is off. But this is a wrong prediction because the reality, the actual state of the switch is actually on. So ideally, the probability here should be higher than this. But we made a wrong prediction because we started with random values for these weights for the neural network. So what should we do? We should, of course, update the weights, right? How do we update the weights? Let's see. What is that we are expecting? What do we want? We want this value to be higher than this, right? So we want this to increase and this to decrease. Ideally, that's what we want, because then in softmax distribution also, this will be higher than this, right? That is what will happen. So how can we increase this? We cannot change the inputs. Input is the same, this particular on state of the switch. What we can do is we can update the weights, especially these two weights. Why? Because these two weights do not influence in this particular case, because for the input x2 and x3, these are 0. So this weight and this weight we need not update logically, right? So one thing we should definitely do is increase this and this, weights of this and this, so that this number increases. Second thing is to decrease this 1.1, we can decrease this 0.5 and 0.6. Why? Again, for this connection and this connection, since the input value is 0, the Wx is 0. This one Wx is 0, this one Wx is 0, but this one Wx is 0.5 and this one Wx is 0.6. So 0.5 and 0.6 we should reduce, and this 0.1 and 0.2 we should increase, right? That sounds logical, right? And how did we learn that? We learned that from the way in which this neural network is working. Simple human logic. So now let us update it. Let us increase the 0.1 and 0.2 to 0.3 and 0.4. And let us decrease the 0.5 and so this was 0.5 and 0.6. It is reduced. Each of them are reduced by 0.2. So this becomes 0.3 and this becomes 0.4. Here each of them are increased by 0.2. So this becomes 0.3 and this becomes 0.4. Now let us again calculate the output. So input is the same. Input has not changed. So now the summation Wx is 0.3 times 1 plus 0.4 times 1. That is 0.7. And here the summation Wx is 0.3 times 1 plus 0.4 times 1 plus 0 times this plus 0 times this. So it's again 0.7. And obviously, if these two numbers are the same, softmax probability will be 50-50. So now this says with 0.5 probability it is on and 0.5 probability it is off. Of course, it's better than earlier prediction, because previously it was saying it's off with a higher probability, but now it's saying equal probability. Although reality, we know this is in the on state, but this is currently better, but still not good enough because we are not still making the right prediction. So again, what should we do? We should repeat what we just did, because what we just did worked, right? So we will repeat the same. These in the whatever connections are going to this second hidden unit, we will reduce this 0.3 and 0.4 and we will increase this 0.3 and 0.4. So further reduce the 0.3 and 0.4 going into the second unit of hidden layer and increase the 0.3 and 0.4 which is going to the first unit of the hidden layer. So let us do that. So we'll increase the 0.4 and 0.5 to 0.5 and 0.6 and decrease the 0.3 and 0.4 to this was 0.3 and 0.4. This was also 0.3 and 0.4. We increase by 0.2 each of them. Here we decrease each of them by 0.2. So now let's calculate. So now the other ones in the black color, I have denoted these weights by black color, these 4, because they do not change. They are remaining the same because it does not influence. So we can see that for this particular input, there is no influence by the bottom 2 connections. So now let us calculate so it should be 0.5 plus 0.6, which is 1.1 over here. And here it should be 0.1 multiplied by 1 plus 0.2 multiplied by 1, which is 1 plus 0.2, 0.3. And now you would already be able to see that in the softmax distribution, obviously this value will be higher than this value. The value here is 0.69, so 69% probability, and here 31% probability for the switch to be off. This is much better, although we are not, the weights are not perfect because it will be ideal if we can say 99, this is 99 and this is 1%. Because the actual state is on. So we want the probability of the prediction to be as close to 1 as possible. But I would say we can still go ahead with this because this is better than the first prediction, which was completely wrong. So we made a correct prediction in this case, although not with the greatest of confidence. Now the question is, okay, this prediction is working for these set of weights. For this input, this is the first input. Will this also work for second, third, fourth, fifth, and sixth input? We have 6 inputs so far. Let's quickly check for each of these inputs, right? So this is the second input. So second input, it's actually on. It's 1, 0, 0, 0. So top 2, if one of the top 2 is on 1, or if both of them are 1, it's an on state. If you remember the initial 2 by 2 matrix. And our weights are the updated weights. So the pink color weights are just from the previous step because we had updated it using the input 1. And so we'll input the numbers, and now let's calculate this. So here the wx would be, w multiplied by x will be 0.5 multiplied by 1, plus rest of the inputs are 0. So none of these weights or these connections going from these nodes have any any significance in this particular example. So the output here is 0.5 and the output here is 0.1 because the weight of this connection is 0.1. Right? And when we apply softmax, of course, since this is greater than this, softmax prediction will be such that this is greater than this. So 60% on, 40% off. Not the highest confidence in terms of prediction, but the prediction is correct. If we were to pick one of the numbers, the biggest number as the prediction is correct. So input 2 also, this neural network succeeded. Now for input 3 here, this time the second one in the column, this array is 1, rest of the ones are zeros. And let's calculate for input 3. So inputs are provided here, and you can see that this node, first node, third node, and fourth node will not contribute. Those connections will not contribute because the input is 0. This one has input 1, which means the sigma wx over here should be 0.6 multiplied by 1. So this should be 0.6. You can see that, and this should be this should be 1 multiplied by 0.2. So this should be 0.2. And again, softmax predicts something like this. This is correct because we want p on to be greater than p off because the actual state is on. For input 3 also we succeeded. Okay, let's check for the fourth one. Fourth one is it's interesting because this is an off state. Actual state is off. Why is it off? Because the bottom 2 are 1. Top 2 are 0. So this is corresponding to off state. So let's feed the input in, and now let's calculate. So now these two these two nodes, whatever way connections are coming from these two nodes have no significance because the input is 0. But sigma summation would look something like this: 1 multiplied by 0.3 plus 1 multiplied by 0.4. It should be 0.7, and here it should be 1 multiplied by 0.7 plus 1 multiplied by 0.8. So this is 1.5. And when we calculate the softmax, this is 0.31 and this is 0.69. Is this what we want? Yes, this is what we want. Why? Because this time the actual state is off, which means this probability should be higher than this probability is what we desire. And that's exactly what's happening. Although not with the highest confidence. Ideally, we want this to be 0.99 and this to be 0.01, but that's okay. But the prediction is correct. And for the fifth input, this is again an off state, 0010. Let's put the inputs. Let's calculate this. So this should be 1 multiplied by 0.3, right? And this should be 1 multiplied by 0.7. This should be 0.7. And when we calculate the softmax, it's 40% on, 60% off. Again, off probability is higher, which is the truth. So we again say we predicted correctly. Very good. And the last input, let's check if this is also successful. We now have a very good neural network. So actual state is off for this input 0001. Input 6, we provide the individual inputs. And now we can see that the sigma wx over here would be 1 times 0.4. This one, so that should be 0.4. And for this, it should be 1 times 0.8. It should be 0.8. And when we calculate the softmax, again, 40% and 60%. Again, we made a correct prediction. So basically, all 6 inputs we were able to predict correctly. The prediction confidence was not high because none of the predictions were like, oh, 90% I know that this is off or on. That was not the case, but still very, very good. Now we have like a very good neural network, basically. So now with this, let's move on. So what we just did is we did not assume any weights. We randomly started with a set of weights and we applied a certain logic based on what output we are producing. And that logic helped us find the appropriate weights, which helped us classify correctly for all 6 inputs. Now what we will see is how this logic using which we found the weights, how this logic can be extended into a mathematical framework so that you don't have to sit and calculate. You can just simply implement a mathematical function. So we'll get into that next. We can generalize what we just did using this 4-step framework. You might have heard of these terms like forward pass, backward pass, loss, weight updation, etc. You might have heard, but let's actually do it on this example. So first we assume random weights and then we do a forward pass. By forward pass, what we mean is we compute the output of the neural networks based on the initial weights that we assume. That's a forward pass. And then this output will not match the output that we are expecting, right? We saw how neural network with random weights initially assigned can produce a wrong output, which we are not expecting. Then there is a loss. That difference between input and output is called loss. And usually we can calculate this loss using different types of functions instead of just randomly, just simply subtracting the predicted output from the expected output. Instead of just doing that, there is a concept called cross-entropy loss. We'll come to that, but I'm pretty sure you might have heard of this. Then what we do is something called backward pass. What backward pass does is exactly the logic which we did. We backtracked what should the weights be such that we can reduce the loss essentially. Like that's what we did in essence. So we calculate the gradient of the loss with respect to each weight. What this means is if the weights change by this much, how much will the loss change? So the way we will be doing this will be using chain rule. We'll come to that. So this is backward pass, and gradient descent is also coming here. Then based on this, in this backward pass, we will adjust the weights. So here in the previous example, we saw how we increased certain weights, increased certain weights and decreased certain weights, right? So we'll update this. So this is essentially what we'll be doing to generalize the process that we just did for training the neural network. So let's go back to our example. In the forward pass, so we are starting with the random weights, right? So this time we'll go through the process of neural network to update the weights. So we are starting with random weights. Random meaning the original random weights, 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8. So let's compute the output of the neural network. What is the output? Output is the two probabilities P on and P off. What is that? It is softmax of Y. What is Y? Y is W times X, the matrix multiplication. And what is W? W was this matrix, X was this matrix, this array, and then matrix multiplication gives a 2x1 array like this, and that produces the softmax. Softmax of that is done, and then it's basically, if we denote this as Y0 and this as Y1, softmax is like e raised to Y0 by Y1 e raised to Y0 plus e raised to Y1, and bottom is e raised to Y1 divided by e raised to Y0 plus e raised to Y1. I think previously we used Y0 and Y0 after we taking softmax, meaning this whole thing we denoted as Y0 and this whole thing we denoted as Y1, I think. But doesn't matter. I mean, we can use whatever notation we are comfortable with, right? So this is the forward pass. Now, in the forward pass, let us now substitute the values. So Y0 and Y1, just before we take the softmax, is this, right? W0 naught X0 plus W0 naught 1 X1 plus this. Bias is not there. We are assuming bias is 0. It's mainly for simplicity. I don't want to introduce bias in this lecture because learning that is not going to make it additionally any more knowledgeable for you that much, but it might introduce a lot of unnecessary complexity in this lecture, which I don't want to do. So then when you substitute the values, what is W0 naught 0.1, naught 1 is 0.2, W0 2 is 0.3, and W0 3 is 0.4. And what was our X0, X1, X2, X3? Our X was 1, 1, 0, 0. That was the input that initially we considered, this one, 1, 1, 0, 0. So X2 and X3 are 0. X2 and X3 are 0. So these two terms will be 0. So it will be this plus this at the top and this plus this at the bottom, which is 0.1 times 1 plus 0.2 times 1, which is 0.3. This will be 0.5 times 1 plus because 0.5 times 1 plus 0.6 times 1. So 0.5 times 1 plus 0.6 times 1 is 1.1. Right? So we get 0.3 and 1.1 here. Then we do softmax. Softmax is e raised to 0.3 divided by e raised to 0.3 plus e raised to 1.1. And this will be 31% and 69%. That is the softmax output. We saw this already, but we are just computing it as part of the forward pass a bit formally. That's what we did. Okay, forward pass is done. Now we will come to the loss. Why is there a loss? There is loss because the predicted output is 1, 0. What does 1 mean? 1 is the on class and 0 is the off class. That is the convention that we will use. So in our input was 1, 1, 0, 0. We wanted the on to be, I just made a mistake. 1 is not the on class and 0 is not the off class. It's not like that. If it is 1, 0, it means it's on. If it is 0, 1, that means it's off. Because we are having two numbers to represent. It's like an array, right? So 1, 0, it's like a one hot encoding. Don't worry if you don't know the term, but basically 1, 0 is on and 0, 1 is off. So this is the expected output or predicted. This is wrong. This is not predicted output. Sorry about that. Let me just edit this. This is true output and this is the predicted output. Right? Okay. So predicted output is actually quite different from the expected output, which means there is a loss. There is a difference between these two, and we can calculate that using our loss function. So our actual state was like this. Input actual state was on. Input was like this. Output is like this. So now let us calculate the loss, and the loss is calculated using cross-entropy. This is very famous. I'm pretty sure you have heard of this, but the equation for that is loss L equal to minus sigma I runs from 1 to C. So C is the number of classes. So I runs from 1 to C. In our case, we have two classes. We are doing a binary classification. So C will be 2. I will run from 1 to 2. Why true I means for the ith class, what is the true expected output? So not for the ith class, for the ith element. So if we have 3 classes, there will be 3 elements here. Since we have 2 classes, the prediction only has 2 elements, right? So I equal to 1 means we are looking at this one. I equal to 2 means we are looking at this one. And y predicted of I means for the ith value, ith index, what is the predicted value? So for the first one is 0.31, y predicted is 0.31, and second is 0.69. And the calculation goes like this: minus 1 times log of 0.31 minus 0 times log of 0.69. So this entire quantity is 0, and this will be minus of 0.5108, that is 0.5108. So this is the loss. This is the cross entropy loss. And you must just take a notice of this equation. And for binary class, it will be minus y. There will be only 2 terms because there are only 2 classes. So if the predicted class and the predicted output and the true output is, let's say, oh, I think I have again made a mistake here. This is, let me copy this. This is the true. Sorry about that. I would rather, make sure that this is correct. So the true output is 1 0, predicted output is 3 1. So I hope I did not confuse you. I just made a mistake in writing this. So true output was 1 here. Y true is 1. Predicted is 0.31. True output here is 0, and predicted is 0.69, and this is the way you calculate. If the predicted output and true output was exactly the same, so if this was also 1 0, which is very unlikely because it's not very common to see with 100% certainty we making a prediction. But basically, if that was the case, loss would be 0. And what's our goal? Our goal is to minimize this loss, because if the loss is minimized, that means the predicted output is very, very close to the true output. Okay. So to make the loss go down, to decrease the cross entropy loss, we do something called the backward passing. So here is where the gradient descent is coming, and back propagation, which we discussed at the very beginning of this lecture, is coming. So let's calculate so this is the cross entropy loss, and let's calculate the backward pass, what it looks like. So let's see what all parameters the loss depends on. The loss definitely depends on the predicted output called y, right? This is small y is the predicted. So loss definitely depends on y, as you see here, obviously. What does y depend on? Y depend on the this softmax function. So whatever inputs we are giving to the softmax function will dictate this y. And softmax will depend on that function's output will depend on the input, which in turn depends on the weights and bias. So these numbers, these weights, 0.1234, 0.5678, these weights and the bias, in this case, it's 0. But if it was not 0, those numbers actually influence this parameter, this quantity. And this quantity determines the output of the softmax. Output of the softmax it changes the loss value, right? So now let's see how to write an equation for the backward pass. We want to minimize the loss. What would that mean? Ideally, we are it's like a local minimum. The only thing we can try to do to minimize the loss is to change the weights, right? Because we are not going to remove the softmax activation function and bring some other activation function. The only numbers that we can change here is, we can of course change the bias, but I'm assuming, for convenience, I'm just ignoring bias. But if bias was also there, the only things which we can change to influence the loss is the weights and the bias. Of course, we won't be changing the inputs. That is fixed. We won't be changing the neural network architecture. Of course, we do that. We do change the neural network architecture in something called as hyperparameter tuning. I'll show that in some time. But once we set the architecture of the neural network in the training process, we are not changing the number of hidden layers or number of hidden units or the activation function or anything else. Those things we are not going to change. So the only thing in this case, what we can do is change is the weight, ignoring bias, and that can hopefully reduce the loss. So if weights influence the loss, then if we can know how much each of these values, W00, W01, 02, and 03, then W10, 11, 12, 13, if each of these how much should we adjust each of these such that we can decrease the loss? Then if we knew that, we could adjust the weights accordingly, right? So let's see how to do that. So loss function, adjusting the weights. If we know how much does changing each W influence the L. So let's say one of the weights influence the loss significantly, which means all we need to do is adjust that weight. So here we have 8 weights, right? Let's just look at the neural network ones. Here we have 8 weight parameters. For whatever reason, let's say this weight had the highest influence on the loss, and all of these other 7 weights had pretty much no influence. If we knew this information, then we don't have to even change these. We can just change this, or we can change these very minimally, the other 7 weights very minimally, and change this one rapidly, like change that so much. So how do we know that? How do we calculate that? We can calculate it such that it could be taking the form of a partial derivative. So dou L by dou W naught naught is the partial derivative of loss L with respect to the weight W naught naught. You can already guess how many such terms will be there. There will be 8 terms because there are 8 weight terms. Each of those weight terms influence the loss. So we should calculate dou L by dou W naught naught by dou W naught 1, etc. So this is how much the weight L, the extent by which the loss L will change when we change the weight W naught naught. And these are the extent by which the loss will change for each of these parameters. So what we really want to do is calculate these 8 terms. And based on that, we'll get an idea how much to change each of the weights, right? So now let's do that. So now let's try to calculate one among these 8 terms. So we had 8 terms, dou L by dou W naught naught, dou L by dou W naught 1, etc., etc. And here we can write dou L by dou W naught as this. What is this? So let's actually have a look at this. So L, which is the loss, it depends on the output of the Softmax activation function. It depends on the input of the Softmax activation function, and also it depends on the weight W naught naught, because and here we are doing a partial derivative with respect to W naught naught. So we are not considering the change in loss that is happening due to change in the rest of the weights. So now if we can write this in a certain format using this famous chain rule, you can see why this is the case. So this is the Y predicted, and this is Z naught. And let me just draw you and show you why this is a sensible way to do this. Let me just take my pen. Okay, so L is the loss, right? L equal to loss. Let's say Z naught is this parameter. So let's say Z naught is the input to Softmax. And W naught naught is the weight. So what this means is the loss is actually the dou L by dou W naught naught. We just need to consider this branch. And the reason for that is W naught naught is this is the connection W naught naught, and W naught naught is not influencing this branch because W naught naught is not flowing here. W naught naught is actually flowing to here. So this this value, this branch is where the influence of W naught naught is there. I understand that this branch terminology is not the right thing to use, but I hope that you get the idea, right? So we can essentially say that dou L by dou W naught naught, dou L by dou W naught naught is equal to the rate of change of L, or partial derivative of L, with respect to the input to the softmax, right, multiplied by how much this input to the softmax changes based on the weight W naught naught. So we can do this product, and this is called chain rule. We are chaining two partial derivatives. So dou L by dou W naught naught that is what's written here. And using this chain rule, now we can calculate the dou L by dou W naught naught. But what is now remaining is to calculate these individual terms. So let's see how to do that. Yeah, so this is the predicted value y predicted 0. This is z naught, and this 0.1 is the W naught naught. Okay. So let us look at the in the chain rule. Let's look at each of these elements in the chain separately. First, let us look at dou L by dou z naught. So L is loss, right? So this is the equation for loss. Loss equal to minus y true 0 multiplied by log y predicted 0 minus true y 1 multiplied by log 1 minus y predicted. This 1 minus y predicted 0 is like y predicted 1, right? Because y predicted of 0 is the predicted value of the top, the first element of the output array. This is the predicted value. This whole term is the predicted value of the second element in the output array. And these two are true, true classes. Like if the light was on, this should look like, in the true sense, it should look like 1, 0. If the light is off, it should look like 0, 1. Okay. And now, if y predicted 0 and y predicted 1 can be expressed in terms of the z0 and z1, because this is the input to the softmax, it will look like this. So z0 is this one and z1 is this, right? So let us actually write that. So this is z0 and this is z1, and this is y predicted of 1, which is also same as 1 minus y predicted. Sorry for my terrible handwriting. It's because I'm writing in this corner. 1 minus y predicted of 1. So that is what you see here. And y predicted of 0, which is this, is over here. And this is W naught naught, right? This is Z naught, this is Z1. So Z naught and Z1 are needed for the calculation of both of the softmax, because that's how softmax works, right? So to calculate dou L by dou Z naught, let's keep these two things in mind: the expression for L and how the y predicted of 0, y predicted 1 depends on Z naught and Z1. Let's keep this in mind. And let's also move on to this second term in the loss. So dou Z by dou W naught naught. Let's look at how that looks like. I'm just coming back to where we left off on our slides. Yeah. So dou Z naught by dou W naught naught is calculated using the original expression for Z naught, which looks like this. So W naught naught X naught, naught 1 X1, naught 2 X2, and naught 3 X3. And now we have L and Z0 handy. Using this, we can calculate the rate of change of L with respect to Z naught and rate of change of Z naught with respect to W naught naught. So let's skip this. We already wrote this. Okay, so now what this would look like is we can calculate dou L by dou Z predicted 0, which is this one. Let me just show you what that is. Oh, just excuse me. There is a small mistake which I made here. I was about to. This is not Z predicted. This is simply Z naught, because there is nothing called as Z predicted. Okay, I'm happy we kind of found it. So dou L by dou Z naught equal to the difference between y predicted not and y true not. How did I get this? This is honestly, when I was making this lecture, I was calculating the dou L by dou Z naught by splitting this into, dou L by dou Y naught. Y naught is this output, right? And then calculating dou Y naught by dou Z naught, because, you can write something like this. Let me show you. So this is Y naught, right? Sorry, where is the pen? This is Y naught. This is Y naught and this is Z naught. So I was initially writing dou L by dou Z naught equal to dou L by dou Y naught multiplied by dou Y naught by dou Z naught. Then I did a bunch of calculations like this, but then later I realized that this is not correct, because the loss actually depends on, we cannot just consider this. The loss, because of the softmax, the loss also depends on this guy, Z1. So writing like this is not technically correct. So we have to consider the fact that we are using softmax here. So this branch, the value in this branch and value in this branch, both branches will affect the output here and here. So we have to consider that while making this calculation for dou L by dou Z naught. And if we do a series of a little bit complicated calculation, we can arrive at kind of like an identity. I would not like to call it as an identity, but it's good to remember that whenever we have cross entropy loss and softmax, so softmax at the output and cross entropy for calculating the loss, we can calculate dou L by dou Z naught using this predicted value of Y minus true value of Y. Right. But if you are really interested how you arrive at this by calculate from basic fundamentals, I can post it as a different side note, but I don't want to include that in this lecture. And dou Z naught by dou W naught is very, very simple. This is just linear dependence. So dou Z naught by dou W naught is literally X naught, which is the first value in the input array. Okay, perfect. So now we have both things. Now all we need to do is like multiply, right? So let me go back to the previous slide. So dou L by dou Z naught multiplied by dou Z naught by this is the loss with respect to the first weight. So this quantity, this term equal to Y predicted minus Y true. This is X naught. So we just multiply this and this to get the total, the loss. And this is the loss term, the first loss term. And how many loss terms like this do we have? We have 8 loss terms, because we have 8, not the loss term, sorry, the gradient of loss. We have 8 such terms because we have 8 different weights. So let us calculate that. Not calculate, let's just write it down. Just give me a moment. Yeah. So dou L by dou W naught, we already calculated the expression for that. We can also write the expression for the remaining 7 terms. So they will look like this. It's fairly simple because it's all about substituting the right what's it called? The right subscript. I'm sorry for blanking, but these are the terms: Y predicted 0, Y predicted Y true 0, Y predicted 0, Y true 0. And this whole term, this part, first part of this, all of these terms are the same. The input value is changing. Here again, the input value x0, x1, x2, x3 are used, but the subscript is now 1. And we know the value of all of these, which means we can calculate the loss for all these 8 terms. Actually, let's see how to do that. So we know the numbers, right? So true value of Y naught, which is the first element in the true value, is 1. So our array, true value of the array is, actually, let me write it so that you know that. So these are the terms, right? Let me just show you. Our Y, the big array Y true equal to 1, 0 if switch is on, and Y true equal to 0, 1 if switch is off, right? In the particular example that we are taking, this is our input array. X naught equal to 1, x1 equal to 1, which means this means the switch is on, right? Because these two are 1. So, and because of that, this is our Y true, how it looks like, which means Y true, the 0th index item is 1, that is this, and the first index this item is 0, which is this. Now, where do we have this 0.31 and 0.69 from? Because we assumed a certain weights, right? And those weights helped us make a certain prediction. And though that these are those predictions, 31 and 69%. And now we can calculate the loss terms using these quantities. So we can substitute the appropriate ones here in these expressions, in these 8 expressions, and we can calculate the loss. And the loss values turn out to be these. Let me go back. 0.6 minus 0.69 minus 0.69, 00, and these. So now what we can do is we can update. So we are still in the backward pass. So where is the gradient descent coming here? Gradient descent is coming because the gradient of the loss with respect to weights is kind of, we are calculating it and moving it behind backwards from the output layer towards the other hidden or input layers, such that in those layers we can update the weight. Right. So this is where the gradient descent and backward propagation ideas are coming. And in the next step, in the 4th step, so we were talking about a 4-step process: forward passing with the initial random weights, calculating the loss in the 2nd step, backward pass or back propagation with gradient descent in the 3rd step. And in the final 4th step, we will be updating the weights. So the weights would look something like this when we update. And just before we update the weight, there is one more thing that you should be familiar with, and that is the learning rate, which is alpha. This is the denotion, the kind of the Greek alphabet used for denoting the learning rate. Let's assume a certain value of alpha, 0.5. There are different values of learning rate which we use when we actually run a neural network in Python. But let's assume alpha is 0.5. So the way in which we update the weight is such that we do the original W00 minus alpha, which is the learning rate, times the gradient, the gradient in the loss with respect to that weight. So in this case, the W00 is originally 0.1. You can see here, we are updating that with alpha is 0.5, and dou L by dou W00, if you remember from the previous slide, let me go back to the previous slide, it is minus 0.69. So we substitute that, and that will give us these values. So W00 will be updated from, it was initially 0.5, it will now increase to 0.445. And W01 will be now updated like W01 minus alpha times dou L by dou W01. Learning rate can be kind of, you can assume it like this. Let's say you are a student, you are learning a book. You are trying to learn a textbook. You read it fast. You might learn a bunch of things faster, but your accuracy is not necessarily going to be very high. So if you are preparing for an exam and if you learn it very, very fast, it may not be the ideal thing. If you learn too slowly, what's the problem? You may not finish all the portions. You may learn a bunch of things, but you will not finish all the portions. So you need an optimum learning rate always. This analogy is also true with neural networks. You cannot have too high or too low of a learning rate. If it is too high, you will not converge with an accurate neural network. If it is too low, you will take forever to converge. You will take a very, very long time. You will need to train again and again and again, right? Run the backward propagation again and again and again. But here, let's update W01. It is increased because alpha was 0.5 and dou L by dou W01 was again minus 0.69, as you remember from the previous slide. So this value gets updated. W02, it has no change. Why? Because the loss did not depend on W02 or W03. Because W02 and W03 in this case had no influence. These inputs were 0. So 0.3 and 0.4 are not going to be updated. It will remain the same. Similarly, let's look at these set of these red color, the weights corresponding to these red color connections, how they get updated. So W10, which is the first one, will get updated from 0.5 to 0.155. So here you see that the weights actually increased, these two weights. But here the first two weights are actually decreasing. And that's because we are subtracting alpha times dou L by dou W10 and dou W11. And if you remember these two terms, dou L by dou W1 and W0 and W1, they were both plus 0.69. So here they were minus 0.69. So because of this, what's happening is the weights are getting updated such that the weights are decreasing. If you remember, the human logic which we used a few moments before, not now, like before we introduced the back propagation, in that human logic, we had identified that, oh, in the first, whichever connections are going to the first unit of the hidden layer, those connections need to increase in weight, increase in the value, those weights, and the ones going into the second unit of the hidden layer should decrease, right? That was based on our human logic. When we do gradient descent, when we calculate the change in loss with respect to weights, we are essentially arriving at the same thing. These two weights are getting increased because these weights are getting connected to the first layer of the first unit of the hidden layer. These two weights are decreasing. They are connecting to the second unit in the hidden layer. And the other two weights will remain the same, 0.7 and 0.8, because this gradient dou L in both of those cases are 0 from the previous slide. Okay. This is excellent because now you know that which weights are getting updated. So W0 is getting updated, W01 is getting updated, 10 is getting updated, 11 is getting updated. These are not changing. These will remain the same. So which are those? The ones getting updated. This will update, this will update, this will update, and this will update. And if these things get updated, will this output probability change? Of course, it's going to change. We just need to see if the change is favorable to us or not yet. That's the only thing that remains to be checked. So let us move on to see the next thing. So let's calculate the output using these updated weights. The updated weights are 0.445, 0.15, 0.545. So these are the two updated weights in these two green connections, and 0.155 and 0.255 in these connections. And when we do this, we can, okay, before even calculating the softmax, I can just calculate this. So this would be 0.445 multiplied by 1 plus 0.545 multiplied by 1. And that is 0.99. And this would be 0.155 multiplied by 1 plus 0.255 multiplied by 1, and that is 0.41. And when we do softmax of these two, we get these kinds of output, 64% and 36%. And is this correct? Of course, this is correct. Is the confidence very high? No, not like 90% confidence, but it's saying 64%. This is the input is on. And what is the actual state of input? It is on. So here we have not significantly decreased the loss. I agree. But at least we made the prediction correct. Initially, the prediction was not correct. So we updated the weights using loss calculation, backward propagation. And then with these updated weights, when we calculate the new output, the output is making the right prediction. This class has the higher probability, and that is actually correct. Neural network is making a correct prediction. So what we just did, I just want you to take a moment and appreciate what we just did here. We simply built a fully functional neural network completely from scratch. This neural network can now make a prediction on an input. If you can try this on various different inputs, not just this one input which I showed, for the remaining 5 inputs, it will hopefully make correct predictions. I don't know, I haven't checked it. If it does not make, we'll have to update the weights according to the loss function that we again calculate, right? So, but for this first input, we calculated the output, and output turned out to be correct. And we did not assume the value of weights initially. We started with a random value. The random value got updated based on the loss we calculated. The loss, the gradient in the loss propagated backwards, and then that updated the weights. And the updated weights is actually now working, at least for the input 1. This is very, very good. We should be feeling so happy at this point. An actual neural network is very similar to what this simple neural network which we just now produced. The only difference is that there may be more hidden layers, and the number of nodes in each hidden layer might be different, and there could be bias in each of the nodes, and there could be activation function at the end of each of these layers, and there could be what else there can be? There will be something called flatten. So there are different changes that can happen to the neural network to make it complex, or make it sufficient for more complex classifications, like let's say cat and dog image classification. It's a complex image. It's not as simple as the image that we used. But essentially what neural network has is, we have already covered that there is input layer, there are one or more, sometimes there won't be hidden layers, and then output layer. The thing that will remain fixed is the dimension of the input layer should be the same as the dimension of the so the number of nodes in the input layer should be same as the dimension of the inputs. So if you have 4 inputs, you will have 4 nodes in the input layer. And if you are doing a binary classification, you will always have two units at the output. If you are doing 10 class classification, at the output you'll have 10 such units, because you need a probability distribution in 10 different variables, right? So these two things will remain fixed, but the number of units here in the hidden layer can be any number. You can define anything. The more it is, the more complex the neural network is, and it can probably handle more complex things, but you will also end up making it unnecessarily complex to train it properly. But the way actual neural network works is exactly same as what we just discussed before. Okay. Now, there is something else which you may have heard of called convolutional neural network. This is called what you see here is convolution. So convolution is nothing but you pass a smaller kind of like a kernel around this matrix. So if your matrix has 8 by 8 or something like that pixels, you can pass a convolution layer around the matrix to convert the image, which may look like this, into a convolved feature which may have a smaller dimension. This has many applications in various image classification tasks, because depending on this type of this convolution mask, you can enable edge detection, you can enable detection of some other features, maybe stripes on the body of a zebra, or what else there can be, edge of like a edge between a river and the sky in the horizon, things like that. So convolution is like a very powerful operation, which we are not covering in this lecture in detail, but convolutional neural network will additionally have this convolution operation happening within the layers in the neural network. And you might have seen cat or dog classifier, or raccoon versus rabbit classifiers, very simple famous classifiers, right? Binary classifiers on Kaggle. There are many other platforms on which you can run such neural networks. All of them essentially work like this. So if the input image is 32 pixels by 32 pixels, this dimension, the number of nodes here will be 32 multiplied by 32. So you'll flatten the image and provide as an input here. Output dimension will be 2. If you are classifying image into dog or cat, output dimension will have 2 units. That's exactly how actual neural network works. But the weights, the bias values, there will be sigmoid activation function and few more things in the hidden layers. There may be multiple hidden layers. There may be multiple units in each of the hidden layers. So that part will not be as simple as what you see in this graphic. And the entire operation which happens in a complex hidden layer, like if you have a complex neural network, you will have a input image, you will operate convolution on top of that. There is something called max pooling. There might be again convolution, again pooling, again flatten, and then there will be a softmax layer to produce the output, and then there will be back propagation, as you see in this cartoon. Back propagation will adjust the weights in the previous layers, and then this will continue in the training process. And after training, you will test the neural network's accuracy with some test images. So test images you will not be using in training. This is how neural networks actually work. But let's not go into the details of all of that, because let us just take a moment to appreciate the ingenuity behind neural networks, which we just observed with a very simple example. All the complex neural networks which you will encounter, ResNet or VGG or ImageNet, there are so many complex neural networks. All of them are extensions of the basic thing which we just built. But the extension, of course, it's easier said than done. But ultimately, it has input layer. It has bunch of convolution, max pooling, flatten. It will have hidden layers, activation functions, and ultimately an output layer. And at the output, you will calculate cross-entropy. You will do back propagation, adjust the weights, and you will repeat this until you are happy. So just before we come to the last part, let's talk a little bit about activation function. Activation function, the only activation function we saw so far in the lecture is Softmax, but there are a few other activation functions which are very popular. Activation function allows us to introduce non-linearity into neural networks. What will happen if we did not have activation function? Our model will be simply a linear model. I'll show you in a moment how that happens. And If we did not have non-linearity, it's very, very difficult to, even if we have 1,000 layers, it's very difficult for the neural network to model complex input data. So we have to have some non-linearity, and activation function magically, or I would not say magically, but it can beautifully do that. And there are a few different activation functions. Sigmoid is a very famous activation function. Maybe you have already heard it. Sigma of x z equal to 1 by 1 raised to 1 by 1 plus e raised to minus z. So if z is minus infinity, this term will be very, very big. So this whole thing will be 0. If z is infinity, then this term will be 0. So it will be 1 by 1 equal to 1. So the minimum value will be 0 when x is z is minus infinity. When z is infinity, the maximum number will be 1. So this is what sigmoid. So sigmoid basically converts any number into a number between 0 and 1. There is another one called tan hyperbolic, tan h, and its formula is kind of similar to sigmoid, but one small difference, it's e raised to x minus e raised to minus x divided by e raised to x plus e raised to minus x. And the range of this will be from minus 1 to 1. And why is that? Because if x is infinity, this term will go to 0. This term will also go to 0. And this will be 1 by 1. So at infinity, the value will be 1. If x is 0, this term will be 1. This term will also be 1. So 1 minus 1 divided by 2 will be 0. If x is minus infinity, then this term will be very big, and this term will also be very big, very big. So this whole thing will be like minus infinity divided by plus infinity. So it's like division of two large numbers and added a minus sign. So that will be minus 1. So that is tan hyperbolic. Another activation function is called ReLU, rectified linear unit. It basically converts all negative numbers into 0, and all the positive numbers will be retained as such. So that is ReLU. So this is how the graph of ReLU looks like. So if z is a positive number, which means max of 0, z, meaning if z is a positive number, ReLU of z is equal to z. If z is a negative number, ReLU of z equal to 0. And finally comes the star, Softmax. We already discussed this. Softmax provides a probability distribution. So it does not have a graph like unlike ReLU or sigmoid or tan hyperbolic. It doesn't have a graph. But you can plot a graph once you know how many inputs are there. Once you input the values, you can plot softmax values for each of those inputs. Okay, so that these are activation functions. Now you might have heard of people saying, "Oh, neural network is nothing but it's a large function." And when I say large, I simply mean here composite function, right? Of course, we can use any terminology, like whatever makes it easy for us to understand. What exactly does this mean? Can you visualize this? Why is it a large function? Let's take an example. What is happening from input to hidden layer? From input to hidden layer, this x is passing. It's going through certain weights, right? So input to hidden layer is basically w1 times x plus b. B is the bias. And on this, we are doing the activation. So sigma 1 is the activation for the first like input to hidden layer connections. And in our example, we did not have an activation for our connections from input to hidden layer. That was to make things easy. But usually there will be activations. So activation is represented by sigma. And here we are not multiplying. This is like a function. So sigma 1 of this. And when we go from hidden layer to output layer, there will be another sigma. So let me just enlarge this for you to see. There will be another sigma. So sigma out, which is W2 multiplied by, W2 multiplied by input to that layer. Input to that layer is the output of the previous layer. Output of the previous layer is this. And so basically W2 multiplied by input to that layer plus the next bias. There will be bias in the next layer also, right? And then you take the sigma at the output. So you can see that there is a cascading of functions here, or cascading of these operations here. And previously I told you that sigma, which is the activation function, is what brings non-linearity into picture. Otherwise, this whole thing will be linear. I'll show you exactly how. So imagine our neural network is very big, right? Then we will have input to first hidden layer. So it will look like this: sigma 1 times w1x plus b1. Sorry, I'm so sorry. Not sigma 1 times, sigma 1 of w1x plus b1. It's just a tongue slip. Then from first hidden layer to second hidden layer, you will have sigma 2 of this whole thing multiplied by W2, W2 multiplied by this whole thing, matrix multiplication plus B2, that's what's shown here. Then that's sigma 2 off. Then like that, in the nth layer, you will have something that looks like this. I don't know why this font size is small. Something that looks like this. So sigma out of Wn times the sigma n minus 1 of Wn minus 1 times sigma n minus 2 of this. This is so activation function. So if you look at this, this is like a cascading of functions. It's literally one huge function, right? So when I say large, I simply mean it's like a cascading of, it's like a function that is like a starting from the nth recursion to the first one. So now let us see why does this mean our activation function can bring non-linearity. Let me just open the pen. Okay. So what we are doing is input from input from the first layer to first hidden layer is something like this, right? So sigma 1 of W1x plus B1. This is what it is. Imagine this sigma was not there, this activation function was not there. Then the output will be simply W1x plus B1. And this output is fed into the next layer. And next layer, what is happening? In the next layer, we do W2 times W1x plus B1 plus B2. And we do a sigma of this. So this is activation function of this. But let's say even here, there is no activation. Then this is fed into the next layer. So next layer would look like W3 multiplied by W2 multiplied by W1x plus B1 plus B2 and plus I need a, okay, this is B1, W2 times this plus B3, right? So so here you can see that what's happening, ultimately what's happening to X is the dimension of, like, what is happening to X is an array. In our case, X was a 4x1 array, right? And what is essentially happening to X is linear transformations. X is getting multiplied. And imagine bias was also not there. For simplicity, right? Bias B2, B3, all of these were 0. What is happening to X? X is kind of W1, X will be some transformation of X. So X will become X prime. Then you will have W2 acting on that. So then W2 will convert this into X double prime. I don't mean derivative here. I'm just saying X is undergoing a linear transformation. So ultimately, this is like just a linear function. There is no non-linearity in it. On the other hand, if this activation function is there, then as you saw in the previous cascading, let me go back. In this cascading, there is always this sigma coming in each of these in each of these cascade, and because of that, non-linearity is introduced. So this is exactly why we need sigma if we want a non-linear function to kind of model a complex input, right? Now let's move on. Okay, so let's move on to this optimization. So you might have heard of neural network training will optimize the neural network, or training will change the parameters in the neural network. What parameters is it changing during the training? Is the number of hidden layers changing? Is the number of units in the layer changing? None of that is changing. What is really changing during training is the weights and the bias. The rest of the things remain the same. And neural network learns the best possible values for weights and bias during the training process. And you might have heard of the term hyperparameter tuning, right? Of course, you have heard of this. So what exactly is that? So hyperparameter tuning will optimize the following. The learning rate alpha, we started with 0.5 earlier, if you remember. We will figure out the best possible alpha for learning rate. We may start with a low number, then go to a moderate, then go to high, and see which alpha is best. We will... oh, sorry, this is not output layers. This is number of hidden layers. Number of hidden layers and number of nodes. So we will be optimizing how many hidden layers are there and how many nodes are there in each hidden layer. That we will optimize. Then we will figure out what is the best possible activation function for our application, whether it's sigmoid, tan, hyperbolic, or something else. Then there are different types of loss functions, cross-entropy loss. You can also just simply take a absolute value, which is a difference between the expected loss and expected output and predicted output. There are different losses which you can take, and we'll be figuring out what works best in the hyperparameter tuning. And there are a few other parameters which we did not discuss in this lecture, like there is batch size, dropout rate, regularization, epochs, optimizer, etc. I don't want to go into details of this in this particular lecture, but when you hear this, understand that these are few other hyperparameters you will be tuning in the neural network architecture. But this tuning will not happen when you are doing the training and back propagation. During a round of back propagation and training and modifying the weights and bias, these things will remain fixed. And what do we really mean by then the neural network architecture? We always hear this, right? Oh, this neural network, I was building a neural network architecture. What does it really mean? It simply means what are the weights and biases, and what are the hyperparameters? Like how many layers out, how many hidden layers are there, how many units are in each hidden layer, what activation function are we using, whether there is flattens, max pooling, etc. is there or not, and what is the loss function, what is the learning rate, all of these parameters plus the values of weights and bias. This whole thing constitutes the neural network architecture. So in very complex neural networks, we will have a lot of these parameters. So obviously we will not be able to write it by hand and do the calculation like how we are doing, which is why we are using programming like Python. So the Python packages basically makes our job easy to calculate all these things for a neural network, so that it can make a complex prediction when it sees a cat, just like how a human baby can say that it's a cat. Here, neural network can also be trained to say that the image which we provided is 85% it's a cat. Let us summarize briefly what we did in today's lecture. The lecture is coming to an end. We had an input image, which was either the images of switch being on or off. And we converted this image into a 4-pixel color image representation. Then we converted that into 4-pixel black and white representation. And then we converted that into numerical representation. And then this 2x2 matrix was converted into a 1D array, right? This 1D array was input. This is the 1D array. This was the input into a function. This function is what was doing the job for us to make the classification. The function looked like this, but it could also be represented as a one single matrix multiplication. We saw that. And this will predict the probability after we do softmax operation. This will predict the probability. So strictly speaking, this y0 is not the probability. I would say the probability is softmax of this. So let me just write that for the sake of P on equal to softmax of this. Softmax of y0 given, of course, softmax of y0 meaning softmax of y0 given y0 and y1. And this will be softmax of y1 given y0 and y1. So this is the probability that switch is on or off. Oh, messed up by my animation, but that's okay. And then we constructed a neural network from scratch, which did exactly same as what our matrix multiplication did. We constructed 4 input units in the input layer, 4 nodes in the input layer, and we had 2 nodes in the hidden layer, and we had 2 nodes in the output layer because we were doing a binary classification. This was 4 because the size of our input was 4/1. And we learned how to optimize the weights, or at least how to change the weight once by calculating the loss function. And we use cross-entropy loss, and we calculated how much the loss depends on how much the loss changes based on the weights, and based on that we found that only these 4 weights need adjusting. So we increase these 2 weights to these values, we decrease these 2 weights, and that resulted in a better prediction. And the better prediction actually was that it was matching with the true state, right? And through this process we learned forward pass, we computed the loss, which was cross-entropy loss. We learned backpropagation, we learned gradient descent, and we learned how to update the weights. So this one slide summarizes everything we did today in today's lecture. And now are we good to answer the initial 10 questions that we were looking at? Let's relook those questions. How did people come up with the idea of neural network? Maybe people came up with it just like how we did, right? I mean, we came up with a basic intuition that, okay, here is a human logic, here is a matrix way of representing this. So, and also there is the fact that in biological systems, things are working very nicely. So maybe representing using nodes and connections will be a good idea. So it seems like a natural progression to move towards neural networks. Neural network math is hard. You already saw that. I mean, it's not easy, but it's when we simplify things, when we take a smaller example, math is kind of possible to understand. So you don't have to be too much intimidated by it. But of course, you can be intimidated by the math of very complex neural networks. But ultimately, at the end of the day, it's the same as a simple neural network in principle. When people say linear algebra and calculus is the basics of neural network, I hope you now understand why that's the case, because we are doing a lot of matrix calculations. We are using chain rule for the backpropagation. We are taking partial derivatives. So ultimately, at the end of the day, this is what neural network is about. And why do we call neural network essentially as a single large function? We have like a cascade of functions, and that function in the absence of sigmoid, in the absence of activation function will be simply a linear function. But to introduce non-linearity in that single large function, we have the activation, and that helps us model more complex things. Although we did not show that using an example, that's why it is used. What is backpropagation? What exactly is propagating backwards? What is propagating backwards is essentially what is propagating backwards is how different is the predicted output from the true output. And that, based on that, we are calculating a gradient. That gradient kind of is propagating backwards for changing the values of the weights. So this gradient descent is basically happening, and it's propagating backward from the output layer towards the weights. So if there are so many input layers, it will propagate all the way back towards the initial layer. And gradient descent is exactly used in this. It is descending in that direction, right? It's for changing the weights. Weights bias, you saw what it is. Weights are getting multiplied with inputs. I mean, weights multiply with inputs. Bias is added to that. Learning rate alpha will decide how quickly the weights change. If you change it too fast, you probably you'll find it difficult to converge. If you change it too slowly, you will have to run the iteration many times. You saw cross-entropy loss, hyperparameter tuning. You saw that. You saw what are activation functions, sigmoid. There was tan hyperbolic. There was ReLU and Softmax. We spent more time on Softmax actually. You saw how chain rule is used. So to calculate the partial derivative of loss with respect to W, we use the chain rule of partial derivative of loss with respect to input to sigmoid, and partial derivative of input multiplied by partial derivative of input to sigmoid with respect to the weight. And when you multiply those two things, you get the total partial derivative, and that is the chain rule. And it is so much useful in calculating the gradient. And the reason why people say neural network is a black box is very simple. When the neural network becomes very big and complex, it is incredibly challenging to visualize all the weights, all the bias. It's very, very hard to even see what is happening inside the neural network. So that is why people say it is a black box. In reality, you know every single weight and you know every single bias. So like if you have access to a neural network, you know everything. It's not like you don't know something what is there in the neural network. It's just that it is very difficult to interpret what those numbers mean. Imagine you have 10,000 weights and biases. How would you make sense of it? So that is the reason why we say neural network is a black box, not because we don't know what's the process behind, the process that neural network takes to make a prediction. We know that because we only engineered this. Right. So I hope now you have a better perspective on neural network. I know that this lecture was a little bit long lecture, but I want to thank you so much for staying. If you have stayed till so much, or if you came back after finishing half of the lecture, thank you so much. I hope this made neural networks a bit more familiar to you than what it was before. And you can also try implementing some neural networks, some simple neural networks in Python. I can share some Google Colab notebooks in the description. But with that, we end the lecture. I thank you so much, and we'll see again in another lecture. Until then, see you. Bye.